Hello, right, here's another circuit analysis question. I've actually done this in a previous video when I was going through the Oxford PAT, so the entrance paper for Oxford for doing physics at university. And I went through this question. I'm going to go through it again, but with a slightly different slant, because now we're just looking at analysing circuits. So I might riff off it a little bit, but this was from the 2015 Oxford PAT. So yeah, let's go through. I'll go through all parts of the question anyway. We've got this resistor array. Now, they haven't connected it up to make a circuit yet. And as is common in Oxford PAT questions, they ask you to work out resistance in various ways of passing current through this circuit. So all the resistors are identical, and they want us to start off by working out the total resistance between A and B. So that's fairly straightforward. We're ignoring C and D. So we can say, right, well, we've got these three branches here in a parallel set of resistors. We've got, well, they're all resistance R. So we've got R on the, wrong sheet. Where am I? We've got R on the top branch. We've got 2R on the middle branch. And then down the bottom here, well, we're going to have half an R for the left-hand parallel pair and then an R. So we're going to have 3/2R. So we just need to add these up in parallel. Now, this doesn't fall into one of our simple ratios, so I'm going to jump to the formula here. So we're going to have a 1/R plus a 1/2R plus a 2/3R, and we're going to have to do 1/that. So we're going to want 6 on the bottom. So we're going to have a 6 plus a 3 plus a 4 to give us 13. So we're going to end up getting 6R/13 by the time we've gone through all of the maths on that. So that starts off fairly straightforward. Then we move on to, they're putting an actual potential difference across that, asking what's the power dissipated in the resistor between B and D. Right, so that's there. So we're going to get, on that particular branch, that resistor is going to have 2/3 of V as a potential difference, because it's 2/3 of the resistance across that branch. And of course, the potential difference is divided in proportion to the resistances. So if we've got our power is V squared over R, we're going to have 2/3 of V. So that's going to be 4/9 of V squared, and then we need to divide by R. So we just stick an R in the bottom. So that's another easy bit. Now we're getting to part C, which is why I've put this question on here, because they're now switching it around for the resistance between C and D. So we're now moving top to bottom here rather than left to right. And this can be quite confusing because we've got a configuration here of the resistors. It's not immediately obvious how we should go about analysing them. Now, some people just say, oh yeah, well, if we were going to try and redraw this diagram, we can say, well, any point on a wire which doesn't have anything, interrupting it, so any point along this wire here connecting C and B is identical. So we could just say, well, let's move C down here and then redraw it, and then that's quite easy to redraw. You've got an obvious set of paths then, that we're either going up here or we're going down there. But I don't really want to do that approach here, even though it works and it's correct, because I think there's something more interesting that we could say about all of this. So say we connected this all up to a circuit. So I'm going to add in a battery. Let's continue this round here. We'll stick a battery in, or a cell anyway, here. So I've turned this into a circuit. And this is now, we're going to have some current flowing through. Conventional current's going to be going this way. And this is going to solve some of our problems of, well, which direction is the current moving in? Particularly when we're considering this middle branch here. Which direction is everything going? Because you see people trying to apply, going around thinking about Kirchhoff's laws and things like that, and thinking, well, how do we go around this circuit? We could go through here, and then what? Are we going back up here? Is that where current's going? I mean, that is a path from C to D, where we go to the left through this single resistor here. Then we go to the right down the middle branch, and then we go to the left down here. I mean, that is certainly a path from C to D, at least in terms of following the wires. Is that a valid path in terms of the circuit and the way that the current might flow? Well, we're going to see no, it isn't. So, right, let's mark on then some areas of potential. So let's go over to blue. So as we're coming out, following conventional current here, as we come out of the cell, so let's draw all of this line in here, all of this. Let's say, yeah, we're at our highest potential here. We haven't used any energy yet. We're at peak potential. So all of this blue bit, let's say we're at top potential. And we only lose potential when we go through a resistor. So all of these wires here, which I'm colouring in quite heavily, all of this is our highest potential, where we've got maximum energy all the way round. Right, let's do the opposite at the other end then. Actually, I will use the red, seeing as I've just drawn over it all. So going out the other side, we can say, right, once we've got to D and we're coming back into the cell, this is all our zero potential. This is where we're at our lowest, all of this red line here. So that's where we're at our lowest potential. Right, so what's going on with the bits that we haven't actually drawn in? Right, I'll put the green on. So if we've come through, we're going around this blue here, and we're going to hit either this resistor, or this resistor. These have got to be, we've got to hit one of those three first. When you pass through each one of those resistors, we've got an energy loss. We've used some energy, been lost to the resistor, and then we're going to end up in some lower energy areas. So I'm going to colour all of this bit here green. This is like our intermediate potential. Now I'm going to ignore, just because I don't have enough colours, this little bit here, that little wire in the middle. So I'm going to ignore that for the moment and just treat these two resistors, this one and this one, as just being like one unit, just to make things simpler on the colours. So now we've got these three different areas of potential. We've got the blue bit. So all of this blue bit is our high potential. All of our red bit is our zero or our low potential. And all of the green bit is our intermediate potential. Now, when thinking about, well, what direction can the current be flowing, we can only go from high down to low. We can't go in the other direction. It has to be going from blue to green, or from blue to red, or from green to red. So we can see now which direction everything's going to be moving in terms of current. So, we've got our current coming out and going in, so that's fine. We also know that current has got to be going that way from blue to green there. It's got to be going that way from blue to green there. It's got to be going that way from blue to red. And then here it's got to be going this way from green to red. So we can see what direction the current can be moving in. So if we were going to then redraw this circuit now, we can use these current directions in order to say what the setup is of going from C to D. So if we've got C here and we've got D there, right, we've got one really simple option of just going straight from blue to red. So let's draw that one down the bottom. If we were just going straight from blue to red, we just got that one resistor at the bottom, this one here. So that's fine. Now, if we're going via the green, then we've got different options. Because to get from blue to green, we're either going through a single resistor, which is the top branch here, or we're going through these two resistors in series. We're going through one or the other. We can't be going through both. And there's no way, once we got to the green, we can't go through one of them and then back from green to blue. So we're going through one or the other. There's no way we're going through both of them. And then once we've got to green, there's only one way we can get to red. And that's to go through this parallel pair down the bottom. So that is our only option. These are all of our different ways of getting from C to D. So just to go through each of these. So from C to D, we could go through the single resistor and a single resistor. So that could be this one and then one of that top one there, or we can do this top one and then that bottom one there. So that's our options there. or we're going through the pair of resistors, these two, and they're now two different ways of going through the bottom branch. So it's just that way of then revisualizing the circuit. So when you get really complicated circuits that you have to analyze, then think about these different parts. As soon as you've gone through a resistor, you've got a potential drop, and that is going to determine the direction that the currents can flow, and it solves the problem of this middle branch. So yeah, I think this is quite an interesting question all in all. So actually, let's work out the total resistance then, just to wrap this up, because it has asked us to work out the total resistance. It was the question. So we've got then, this is going to be, let's change color again. So we've got a half there of R. This is going to be 2/3 of R, because we've got our 2:1 ratio. And then we've got 1 at the bottom for R. So we can add up a half and 2/3. So that is giving us, what's that giving us? 7/6, isn't it? So we're now going to have to put these into our formula. So we've got 6/7R plus, 6/7R plus 1/R. So we're going to want to get these over a common denominator, which is that. So we're going to end up getting 7/13R. That's going to be our final resistance for all of that. So yeah, I mean, those actual sums are fairly straightforward. The interesting part is redrawing this circuit, which is why I wanted to do this video again with extra emphasis on the different coloured regions of high, low and medium potential.